Welcome to the fifth video on our module on data-driven distribution system planning. In the last video, we introduced our synthetic data generator, customized for energy data. My name is Pedro Vergara, and today we are explaining how synthetic data can be used to improve distribution system planning. Let's start with understanding the added value of synthetic energy data. When generating synthetic time series energy data for planning, we expect the data to closely resemble the original data statistically. This means, specifically, peaks values, not only the magnitude but also when they occur. These are often low probability events that are critical for system design and operation. Average or annual energy consumption. This is essential for energy planning, as opposed to just power planning. Energy behavior. Capturing high and low demand periods is crucial for quantifying flexibility in the system. We also expect generative AI models to generate future demand profiles based on a specific condition, such as weather forecasts or annual energy consumption trends. Handle multiple technologies like heat pumps and photovoltaic systems, as well as different aggregation levels, such as individual houses or entire substations. Manage data at multiple time resolutions ranging from 1 minute to 1 hour or more. One of the powerful features of generative AI models is their ability to use conditioning. This allows us to generate future demand profiles based on specific outputs, such as weather forecasts, maximum peak demand, or average energy consumption. However, a key challenge arises. How do we translate an annual increase, such as a 5% growth in energy demand, into a daily profile? Let's see how we can use conditioning in the context of distribution system planning. In the context of distribution system planning, short-term planning is often referred to as hosting capacity. Hosting capacity answers the question, what is the maximum increase in demand and/or the number of distributed energy resources that the current infrastructure can handle? This maximum is typically defined based on technical metrics, such as voltage threshold or cable capacities. However, this traditional definition often disregards the risk of reaching such technical limits. The general approach to data-driven distribution system planning involves three key steps. First, sampling. Generate a large number of synthetic demand and distributed energy resources profile. These profiles can be conditioned on future scenarios, such as annual energy consumption. Second, simulation. Run power flow simulation for each scenario to assess the system performance under different conditions. And finally, analysis. Estimate the technical performance metrics from the simulation data, enabling a statistical analysis of the system behavior. The proposed data-driven framework allows network operators to plot the figure shown in the slide. We call this figure as operating regions. In this figure, each point on the graph represents a combination of demand and PV generation increases, aggregated across all users or substations. The time component is disregarded, meaning that we could reach a given point in 1, 2, or 5 years from today. The technical metrics used in this analysis are derived from multiple simulation scenarios, providing a robust basis for decision-making. Let's consider a practical example. As you can see in the figure, at 40% annual energy growth rate relative to today, the system can accommodate a 26.5 increase in PV generation without violating voltage magnitude constraints. However, if we exceed this limit, voltage violations will likely occur. This raises an important question. What happens if we increase the design risk? In the context, we define risks as the percentage of simulated scenarios in which voltage magnitude violations are observed. Based on this, if 5% risk is allowed, the distribution system PV hosting capacity increases to 42.3%. This means that we gain 15% more capacity with only a 5% increase in risk. This example shows how planning considering risk allows for a more efficient use of the current infrastructure. Remember, we allow risk of voltage violation during planning. This doesn't mean that voltage violation will be accepted during real-time operation. Solutions to deal with voltage violation during operations are available, for instance, PV panels disconnection. To summarize, we need to move beyond deterministic planning approaches. The complexity of the energy transition is challenging traditional methods, and we must adapt. By incorporating accurate modeling of generation and consumption data, we can reduce uncertainty and make better informed decisions when considering risk. However, one challenge remains: the visualization and explainability of such large amounts of data. Making this data accessible and understandable to stakeholders is crucial for effective planning. Thank you for watching, and I look forward to seeing you in the next session.